Here in this introduction to systems of linear equations, I want to remark again this in the case of two variables, and we can imagine the system xy, right? And any straight line in this coordinate system can be represented by such an equation. Here, ABC are constant coefficients. So any line that is, no matter a line with a positive slope or negative slope, or even a vertical line, so no matter which line, they can be represented by an equation of this form. This is a linear equation. Yeah. Imagine the geometric feature of, that is a line, right? This represents a line. So equation of this form is a linear equation involving two variables, x and y. That is, every point on the line will satisfy this equation. And if you have two variables, you don't have to call them x, y. You can call them x1, x2, as I discussed in my previous lecture. So here you might have an equation involving three variables or even n variables. N can be as big as 100 or even 1,000. So here, because that means you can consider an equation involving many variables. So a linear equation is defined by this form. x1, x2, xn are the n variables of the equation. And here, the coefficients are x, a1, a2, an, and b as a constant on the other side of the equation. So as we looked at earlier, so here you have two equations, and the first equation is just a line, right? If I try to graph that, so this is x1, this is x2. As you can see, x2 is negative x1, so it's just like, right, like a y equals negative x, right? So the line, if I draw the line, is a line with a -1 slope. And the second equation is the same as x2 equals negative x1 plus 5, if I rewrite the second equation. So that means, well, this equation, if you are more familiar with xy notation, so you can write x2 as y. For example, this will be the same as y equals negative x plus 5, right? That's a line with a slope of -1, y-intercept being 5. So let's draw that one. It's being 5. Slope is still -1. So as you can see that the two lines are parallel because they have the same slope. So they have the same slope, which is -1. And the y-intercept of the first line is 0. For the second line, it is 5. So these two are parallel lines, and they will never intersect with each other. That means a point on this first line cannot be a point on the other line. That means whenever it is solution of the first equation, it cannot be solution of the second equation. So we have no solution. And the second example, we solved it in the previous lecture. So we know we have one and only one solution. So this first equation, if you want to think this in terms of y, that is in terms of x, that's actually x plus y equals 0, right? If those are the names you're more familiar with, then you can try to view it this way. So y is negative x. Okay, that is the line with the slope of -1. But try to get used to the new notation. So if I call x1, x2, we can also look at, so x2 is negative x1. So that is just the same. The first equation represents a line. So if this is my x1, x2, the line with the slope -1. So this is, yeah, every point on this line will satisfy this equation, first equation. A second equation. So, okay, we just drew the solution set of the first equation. And second equation, if you rewrite the second equation, let's draw a line. So the second equation can be written as x2, because first equation is written as this, right? The second equation, x2 is equal to, I can put x1 on the other side, plus 8. So you see, second equation has a slope +1. So slope is positive with the 8 as y-intercept. So +1. So I'm going to draw slope with positive with y-intercept as 8. So these two lines, they have different slopes. They must intersect. There's only one point of intersection. So there's one point that is common to both lines, and that is the unique solution to the system. So we just do with the geometric meaning of the solution, right? We found one point, yeah, for the system. So that is second system. This second system, of course, we have many solutions for the first equation, many solutions for the second equation, but there's only one solution for the system. That means only one point that is common to both equations. So a third case is, okay, again, a system of two equations. And if we try to visualize the solution set, as we noticed, this first equation, if I multiply it by 4, right, I will get 4 times 3 is 12. So you see, the first equation is the same as the second equation. That means they both represent the same line. So we can convert the first equation into second equation. So let's draw it. So that means if I draw a line represents the first equation, so that is this line, because -1 as a slope and 3, +3 as y-intercept. And the second equation is exactly the same line. That means every point on the first equation, every point on this line will be a point on the other line, because they're the same line. that is every point satisfies, okay, every point that satisfies the first equation satisfies the second equation. So how many solutions? Every point will satisfy both, right? Because the both are the same system. So every point on this line will be a solution. So that's how many? Infinitely many. So we have infinitely many solutions for the third system. So the solutions are many, as long as it is a point on the line. Yeah. So we have three cases. Either no solution. So imagine two parallel lines, they never intersect, right? There's no common point that will be on both lines. No solution. One solution. There's only one solution. That means there's a unique solution. Imagine two lines that intersect. So there's one intersection point. That's the only solution that is common to both equations of the system. And it's also possible there are infinitely many solutions. If in the case of two equations, if the two equations represent the same line, then every point on the line will be a solution because they satisfy both equations. So three possibilities. It happens that when we have a larger system, we still have the three possibilities. Right now I tell you, but we will see it. We will understand why in the near future. So now at least you just saw the geometric meaning of is zero solution, one solution, or infinitely many solutions using the straight line relationship as illustrations. So now let's look at a very general case. This general case is that I want to look at this equation of n variables. As a matter of fact, you saw this definition earlier. So this is an equation of n variables with those coefficients of these variables. So this is only one equation. What if I have another equation involving these n variables? So we need, for example, let me write again a second equation involving these variables, right? x1, x2, xn, and there's a b. Oh, but I want to say that the coefficients may not be the same. One might be different than the coefficients in the first equation. Yeah, depending on the problem, right? So we want to represent more than one equation. If our system has more than one equation, then how do I use proper notations to represent the second equation in the system? So if I put A1, A2, AN equals B, then that's not correct because I assumed that the second equation is exactly the same as the first equation. So we cannot assume the second equation is the same for a general system of two equations, right? We cannot do that. So in order to make a generalization, and we will introduce, for the first equation, I need to add a 1, you see? This 1, B1. That means all the coefficients of those variables and the constant on the right-hand side of the equation. Okay, the coefficients in the second equation, I will use a 2. So 2, 1, 2, 2, 2, 2n, B2. You see that addresses the problem. If I have more equations than 2 equations, then I can always do that. Right? We can always introduce another subscript. So based on this, let me show you a general system. This general system, do we realize in the first equation, you see you have this 1, that's first subscript of A. That means the coefficient in the first equation. But the second subscript means it is the coefficient of first variable, coefficient of the second variable, coefficient of the last variable. So this A21, A22, A2n, those are the coefficients of the n variables in the second equation of the system. So add a 2, B2. That's the right-hand side of the second equation. And a total of m equations. Let's assume we have a total of m equations. So in the last equation, which is the mth equation, then the right-hand side will be bm, right? So this bm is not necessarily the same as b2, not necessarily the same as b1. So we just want to represent a general system. So we just give a form that is a system of m equations. And the coefficients will be m1, m2, mn. That's the m1 coefficient of x1, m2 coefficient of x2, mn coefficient of xn. So all these are the just equations with coefficients involving the same variables, same n variables. So you see a system of how many variables? N variables. How many equations? M equations. That means the number of equations, you see from 1, 2, 3, 4, all the way to m. M equations, how many variables? 1, 2, 3, 4, all the way to xn, n variables. So n and m may not the same. They don't have to be the same. So it's just a system we see kind of very general. That means we have such a system. Maybe it's a system of only one equation, maybe m equations, right? So involving n variables. Now I want to extract only the coefficients. So let's see in the system. Okay, I do not write the variables. And then we can see the first row, list of numbers, and we see just those numbers. Here in the first row of a rectangular matrix. And then next, just take out all the coefficients and also the right-hand side number. Then we get second row of a matrix. And then how many rows? We can get a total of m rows of matrix. So because I have a total of m equations, right? So the last row of the matrix will be those numbers, am1, am2, amn, bm. So you see we have a matrix. This is a rectangular array of numbers. And this matrix, we call it an augmented matrix of the system. So actually, if you have augmented matrix of the system, and you can tell the right-hand side of each equation and how many variables in the system, because this is the coefficient of first variable, coefficient of second variable, coefficient of the nth variable. So we can tell there are n variables in each equation, right? Because we see in each equation we have n variables. The right-hand side is just a constant. Yeah, it's not a coefficient of a variable. So we do have this standard form, and from the standard form, we can see a rectangular array of numbers, which is called augmented matrix. So we also can have a coefficient matrix. Suppose I have only a matrix that is this part without including the right-hand side. So if the only difference is that this part, we take only this part. Yes. And then we get this matrix. That means without thinking of the right-hand side. So this is the coefficient of each variable. So this is the coefficient of x1, coefficient of x2, coefficient of xn in the first equation, right? Coefficient of x1, coefficient of x2, coefficient of xn in the second equation, and etc. Then we have coefficient of x1, x2, and xn in the last equation, the mth equation. So here, just the coefficients of those variables in the m equations. Then we call it, this matrix is just a coefficient matrix. So you have two matrices. One is called coefficient matrix. One is augmented matrix. Yeah, so this is augmented matrix because it has the right-hand side as well as the coefficient, all the coefficients. So let's see, this is a very friendly problem because if I want to show the coefficient matrix, it will be this one. Because as we can tell, this is 1, right? That's a 1, although you don't have to write 1. 1 times x1 is still the same. So this is a negative 1. So you see we have, for the first equation, 3 coefficients. 1, 1, negative 1. For the second equation, we don't see the x1 variable. If we do not see the x1 variable, that means coefficient for x1 is 0. We do see x2 variable, coefficient of x2 is 1, right? So then we can see the second equation, we have 3 coefficients. They are respectively 0, 1, 1. Yeah, 0, 1, 1. And third equation. Third equation, do we see x1, x2? No, we see only x3 variable. So that means x1 variable doesn't appear, and we have a 0 coefficient. 0 coefficient for x2. Okay, so that is 0, 0, 1. The coefficients for the 3 variables are 0, 0, 1. So when you do not see a variable in a certain equation, then the coefficient is 0. And the matrix see a lot of zeros. That's nice because usually it means the equations are relatively simple to solve. But this is just to know this is the coefficient matrix and this is the augmented matrix because 2, 3, 1 is also listed in the matrix. So that is the right-hand side of the system, 2, 3, 1. So that is the last column of the matrix. So we see that for this example, coefficient matrix, augmented matrix. And can we solve it really quick? Yes, we solve it because it looks like we can quickly get x3. x3 from the third equation is obvious, right? x3 is found. If it's 1, then I can immediately substitute 1 into the second equation. That means if x3 is 1, x2 can be found because x2 plus x3 is 3. So what is x2? x2 can be found. X2, once we solve it, we get from here, x2 will be 2. 3 minus 1 is 2. Okay. So now we have both x3 and x2. Now go backwards. And can we do, okay, solve one more variable because if we know x2 as 2, right? So let's put a 2 here because x2 is found. x3 is given actually in the third equation. And what is x1? So let's see that x1 is, after we subtract 2 from both sides, you see x1 is just 1, right? Add 1 both sides. So x1 is 1. So now we have a unique solution because we found x1, x2, x3. Don't think that you found 3 solutions because x1, x2, x3, this 1, 2, 1, right? So that is the value of each variable. And this is one solution because we have to find value of all variables in the system. So we found value of each variable. That's only one solution. So these values will satisfy all 3 equations of the system if you do a double check. Yeah. And in that case, that will be a solution. And it's the unique solution, a unique solution of the system. And most importantly, this system is very easy because it's a triangular form. The coefficient matrix has a triangular form. Look, coefficient matrix, right? We have some zeros, then I can draw this. So lower triangular entries are zeros. Yeah, so I mean this. So, and that's why we can do the backward substitution to solve the system and find easily the solutions. So from this, we can get some insight. That means a system with some zeros seems easier to solve. What if a system is dense? That means if we do not have as many zeros as we want, then we can try to eliminate variables to get a coefficient matrix that is in a triangular form or something close to a triangular form. So if possible. So that is the idea. We are going to look at a system. And this is a system. From this system, our goal is to eliminate variables. Let's see, can we possibly eliminate it to such an extent that we get uh, we eliminate x1 variable from the second equation, eliminate x1 variable from the third equation. And just because of our previous example, you see, in the previous example, you notice we have x1 variable, right? There's no x1 variable. There's no x1 variable in the third equation. That is a very easy case to solve. So, and we hope we get the similar situation, that is, we want to eliminate x1 variables from the second and third equations. And afterwards, we can try to eliminate x2 variable, right, from the third equation. Then we can hopefully get something like that or something similar to that. Okay, let's try. So this system, I want you to figure out the strategy of eliminating x1 variable. That means we don't have to do anything to the first equation. We just keep the first equation as is. Keep it. So I'm going to write the first equation. Second equation, yes, we need to change. That is, I want to eliminate the x1 variable, but I want to make use of the first equation. Although I don't change anything, I don't make any change to the first equation, but I can use the first equation. Suppose I use it in such a way that I multiply it by 3, and then I subtract first equation from the second. The second equation becomes what? So now the second equation, let's call it second equation. That is the first equation, new version of the first. So can we do the subtraction? Yes, let's do second minus first. Let's see what happens. Second equation minus first, immediately x1 is gone. X1 is eliminated because of they have the same term, right? We eliminated. So then second equation minus the first equation, there's a negative 7 x2. Second equation minus first equation is negative. Okay, I need to line up. That is, I need to put negative 7x2 here. And just so it's neat, minus that is x3. Do a subtraction. Second minus first. So negative 1 minus 9, negative 10. So this is the second equation. So you see what I did is to the second equation, right? I eliminated one variable. Third equation. So now I still have the first equation I can use. So how do I use first equation now? I can make good use of the first equation and revise the third equation. So let's suppose I compare the third equation with first equation. And in order to eliminate x1 variable, I hope this is a 2, right? So let's put a 2. Okay, 2 times first equation is a 4, 2, 6. Yeah. So I multiply the first equation by 2 and then do a subtraction. So this is now third equation minus first equation times 2. As a result, I can eliminate x1 variable. So you do a subtraction, x1 variable is gone, and this minus that will be negative x2. This minus the other one will be, you see, 1 minus 2, right? So negative x3. And this 4 minus 6 will be negative 2. So now I have a new system. And the next two equations are no longer involving x1. And we actually achieved the elimination of x1 variable from the second and third equations. How did we do that? Just second equation minus multiple of the first equation. What multiple? It's a 3 because of this, right? This 3. So multiple of the first equation is subtracted from the second equation. Multiple of the first equation is also subtracted from the third equation. What multiple depending on the variable coefficient, yeah, of each equation. Okay, so now you got this experience, and then let's go ahead see what we do now. So you realize the equation now becomes a new form. And if you look at its augmented matrix, augmented matrix is so I'm trying to show the system together with its augmented matrix. Yes, this one. This is the corresponding augmented matrix. You see, 1, 2, 1, 3, 1, 2, 1, 3, and 0 in front of x1, right? Because x1 is gone. So x1 has a coefficient 0. So 0, -7, -6, and -10, the right-hand side of the second equation. And then the third equation, 0 as a coefficient of x1, -1 coefficient of x2, -1 coefficient of x3, and -2. Okay, so that's our current system. So we can go from here. You see the correspondence. What is the advantage of writing the augmented matrix? Each system has a unique augmented matrix, assuming we have the standard form, right? The right-hand side is only a constant. So you can put it in the augmented matrix form. And you don't have to write those variables. It's a really cleaner and more convenient. But I know this is new to you, but as you get used to it, you will prefer this way to represent a system of 3 variables. You see, coefficient of first variable, second variable, coefficient of the third variable in the first equation. So you know augmented matrix of this type will involve 3 variables. So all these are the coefficients of the first variable, x1. Those are the coefficients of the second variable, coefficients of the third variable in 3 equations. Now, continue to do more eliminations. So if we go from here, then we can use second, third. But actually, second, third, I can swap. The system doesn't change if I swap the two equations, right? So that is equivalent to swapping the two rules. You see? Second rule becomes the third. Third rule becomes the second. Yeah. So we swap two equations is the same as swapping two rows in the augmented matrix. So let's do a swapping. Then what happens is after swapping, also we can do some more changes. That is, I can rescale. That is, multiply the second equation by a -1 because I don't like the negative coefficient. So we multiply it by -1 both sides. So each term times -1 becomes a +1. So after swapping, I multiply it by negative number, constant, right? Or positive. It doesn't matter. As long as you multiply it by a non-zero number, then we call it a scaling operation. So it becomes positive. You see, that's the second equation. That's the new second equation, not this one. And that's all. So far, do you realize very simple operations we've done to the system? Swapping two equations means swapping two rows of a matrix, right? Scaling, that is multiply an equation by the non-zero constant, both sides of the equation. That is same as multiplying a row by a non-zero constant. That means each entry of the row by a non-zero constant. So yeah, so just like what we did from here, we swap two equations, then the first equation stays where it is still, and second equation will be placed here. Third equation will be this. So that's swapping two rows. Means swapping two equations. And then as now the new second equation, we can do a scaling. That is, we multiply each entry of the second row by a -1. So 0 times -1 is still 0, right? The second row will be, 0 times, the next one times -1 will be positive. And then positive, +2. The second row will become this. And the first row will be same as before. We don't do anything. Third row is same as before. We don't do anything. But you can also do scaling if you want, right? You can multiply it by -1. So you can do this if you want. I just want to show some scaling. And you can even multiply it by any non-zero number. It's also called a scaling. That is a type of operation because it doesn't change the system. You get equivalent system. That means we do not modify the problem, although they look different. Now you can go on, and so now we have this far. What can we do? If we look at first equation, we keep as is. Second equation, but we want to eliminate the x2 variable from the third equation. So we can have a triangular form. And to eliminate x2 variable, what do? I can make use of the second equation. you might wonder, why don't we use the first equation? Well, think about if you use the first equation, it's so possible to try, then you might possibly introduce a variable, right? If you do an operation with the third equation, then you can get back the new. When you eliminate x2 variable, you may introduce x1 variable back. So that's not what we want. So, okay, so let's take advantage of the second equation. And what do? We don't have to do anything. We don't need to modify the second equation because we just keep the first equation as is. Keep the second equation as is. But the third equation is the equation we want to modify. So how? So we want to add a multiple of the second equation to the third. Add what multiple? The second equation, you see, if we put a 7 times 2 is 14, right? So if I add this, so this is what we are going to do. That is 7 times the second equation is being added to the third equation. So a multiple of the second equation is being added. Then the x2 will be eliminated in the third equation. So we get a new third equation. So when we add these two, we get 7 plus -6, which is, and 14 plus -10 is 4. So now, after we do this operation, a multiple of the second equation, which is a 7 multiple of the second equation, and then you can eliminate x2 variable, then you get a new equation. Now, do we get a triangular form? Yes. And this is the equation system we can solve because once you get the x3, the value for x3 is obvious, right, from the third equation. Once you know x3, you can put it into the second equation, you can get x2. So do the backward substitution. So from x3, you can get x2. From x3, which is 4, and then you solve for x2, right, from the second equation. So x2 can be found as, if 2 minus 4 is -2, so we get x2. Now, once we get x2, because x3, they're both known, then we can get x1 from the first equation. So just substitute x2, which is -2, into the first equation, x3, which is 4. And so everything is known except for the x1. So then from the first equation, we can find x1. So you can see that the first equation is actually the same as x1 minus 4 plus 4 is 3. So x1 is simply 3. Yeah. So we get how many solutions? A unique solution. Yeah, although you get 3 numbers, there are numbers for 3 variables. So actually that's just one unique, one value for each variable. As we see that we got through the backward substitution method, we got a unique solution, which is 3, -2, 4. So let me write it in this okay, so let's just to see it's 1, not 3, so you can organize your solution in this form. So either in the vertical, like a vector form, or just group the three values to indicate that 3 is the value of x1, -2 is the value of x2, 4 is the value for the third variable, x3. So because solving a system, you have to find all variables, right? You have to solve for the values of all variables. So then once you find values of all three variables, then you find a solution. But that's the only solution to the system of three equations. Because this, you can check, it satisfies all three equations in the system. Okay, so three operations, and they are called scaling and interchange of two equations, or interchange and then two rows of an augmented matrix. Scaling means multiplying an equation by a non-zero number, or for the matrix, multiply a row of the matrix by a non-zero number. Replacement. Replacement is to replace a row. For example, when we try to eliminate a variable, right, we replaced that equation. How do I replace? We replace a row of the matrix by adding multiple of another row to this row. Yeah, so you see I use the operation for the equations, or operation on the matrix, because they are essentially the same, right? Three operations. Okay, so just one quick remark. So if you want to see in the very first step, when we wanted to eliminate the x1 using, so we kept but we want to get a new second equation. What did we do? The old second equation minus 3 times first equation. Notice that when I use a parenthesis, here means the equation number. Equation number 2. Equation number 1, I use parenthesis. The 3 means just a number. You can also look at this. The reason I do this is because it's a multiple of the first equation being added to the second equation, right? To eliminate this. Why do I choose -3? Because the multiple of the first equation, if we use that -3 as multiple of, constant multiple for the first equation, then we can create the opposite coefficient for x1. Then you add to the second equation, you will cancel x1. So the goal is to eliminate x1. Therefore, the multiple of the first equation, we want to choose a -3 as the multiple. But even though you use that multiple, you do not modify the first equation. You still leave the first equation as is only to be used to modify the second equation. Okay, so that's so as long as we keep the goal in mind, then you will see, keep the goal in mind. You see the first equation doesn't change, right? Second equation, yes. After second equation, a multiple of the first equation is added to the second equation. Second equation is affected. Okay, so just remember the three operations. That's all you need to simplify a system. Step by step, each step, they look different, but the new system is equivalent to the old system. That means we do not want to change the problem. We're still solve the same problem, although they look more and more, they look simpler than before. Step by step, we want to make the solution evident to us. So gradually we simplify to such an extent that we can solve easily. Okay, that's all you need to know for the for time being. 3 operations. You need to know how to apply them to simplify a system, and how can you use augmented matrix instead of equations. Yeah, if you know the matrix is corresponding to the system, right? You don't have to write variables all the time. So let's get used to it.